Page 5 of Vector Apps Addendum. Number 11. Find the equation of the plane through these 2 points, 1, 2, 3, and 0, negative 1, 2, which is parallel to the x-axis, the y-axis, and the z-axis. Okay. So let's picture this. We have a coordinate system, 3D. Here I've marked the x-axis with yellow, and I've drawn an approximation of the points A and B, and I've drawn a plane through it which is parallel to the x-axis. Okay, so the jump you have to make here in thinking, and I don't think this is really obvious, but if you drew a vector that is parallel to the x-axis on your plane, you can see that actually if I drew perpendicular to the green and the orange vectors here, I would get a normal, right? And so basically what you need to do here is you need to take the x-axis vector, which we could represent as 1, 0, 0, and you take your vector AB, which is the orange vector, and if we find the cross product of that, we can find a normal vector. Okay, so what we're going to do first is we're going to find the vector AB, which is equal to 0, negative 1, 2, and we're going to subtract vector A from it, and we'll get negative 1, minus 3, and minus 1. So that'll be the AB vector. And then we're going to find the cross product between the AB vector and the x-axis vector. And that will give us a normal vector, which will allow us to find the equation for the plane. So this will be 0, and this will be negative 1, positive 1. Negative 3, because 1 times negative 3 is negative 3, minus 0. So this will be the normal vector of the plane. So to complete the equation, all we need to do is write down the left side of the equation, which would be 0x plus 1y minus 3z, and then we just set this equal to the coefficient 0, 0, 1, negative 3 times one of the points. For example, 1, 2, and 3, which is point A. Okay, and then we just find out what that equals to. So it would be 0 plus 2 minus 9, which is equal to negative 7. I'm just going to erase this here. Okay, so that's equal to negative 7, and that's our equation. Y minus 3z equals negative 7. So now we're going to do the same thing with the y-axis. So we take the y-axis, of course, would be written as 0, 1, 0, and we're going to cross product the AB vector with that. We're going to cross product the AB vector with 0, 1, 0, and that'll give us, first number would be minus negative 1. Second number would be 0 minus 0. And the third number would be negative 1 minus 0. So the coefficients in the left side would be 0, negative 1, 1, 0, negative 1. The coefficients on the right side would also be 1, 0, negative 1. What we put on the left side are the variables x, y, and z. What we put on the right side are the numbers for one of the points. So we'll use 1, 2, 3. And then we just simplify. So x minus z equals 1 minus 3. X minus z equals. Now finally we're going to do the same thing to the z-axis. So again, we just take the AB vector, which is negative 1, negative 3, negative 1. We cross product it with 0, 0, 1. That gives us negative 3, negative 1, positive, and 0. So we have 3, 1, 0 as the normal. So we'll put those as the coefficients on the left side and the right. And then on the left side, I multiply those coefficients times x, y, z. And on the right side, I multiply those coefficients times the coordinates of A. Just add everything together. And then the left side simplifies to negative 3x plus y equals, and the right side becomes negative 3 plus 2, which is negative 1. So basically we end up 3x minus y equals 1. Number 13, this one is not so bad. We take, we say the point 1, 2k lies on this plane. So that of course means that 1, 2, k, these values have to satisfy this equation. So to find the value of k, all we need to do is substitute in 1, 2, and k into the equation. So we're going to have x plus 2y minus 2z equals 8. And in these blanks, we're going to put 1, 2, and k. So we're going to have 1 plus 4 minus 2k equals 8. We're going to have 5 minus 2k equals 8. Negative 2k equals 8 minus 5, which is 3. So k is equal to negative 3 halves. Okay, so that's part A. And part B says the coordinates of B such that AB is normal to the plane, and B is 6 units from it. So I'm just going to draw a picture here. I got the plane, I got A, which is on the plane, and then I'm going to draw B, which is a point normal to the plane, or the line AB is normal to the plane, and B is 6 units from the plane. Okay? So the key here is we already know the normal vector to the plane because the normal vector can be found by looking at the coefficients of the plane equation. So we know that the normal vector of the plane looks like 1, 2, negative 2. Okay? So we know that AB is parallel to that. So if we know AB is parallel to that, we could just say that the points on AB, on line AB, could be found by taking the coordinates of A, which are 1, 2, and negative 3 halves. We'll use that for the initial position. And then we'll add lambda times the normal vector. So using this equation, we could find any point along AB, including the point B. Okay? Basically, we know that this point here is 1, 2, negative 3 halves, and we want to know how many lambda should be so that we could get to point B here. So what if we just did this? What if we took 1, 2, negative 2, and we figured out how long it was, and then we scaled that into a unit vector, and then we multiplied by times 6 to see what AB should be. Okay? So let's take 1, 2, negative 2. And we'll find out how long 1, 2, negative 2 is. And it turns out that it is square root of 9, which is 3. So now we know that this vector is 3 long. If it's 3 long, then if we divide it by 3, then it becomes a unit vector, right? And actually we want it to be 6 long. So if we want it to be 6 long, then we should take the unit vector and multiply it times 6. So that would be 6 over 3, 1, 2, negative 3, which is actually equal to 2 times 1, 2, negative 3. Okay? I'm sorry, it's 1, 2, negative 2. 1, 2, negative 2, 1, 2, negative 2, and 1, 2, negative 2. Okay, so basically lambda equals 2, right? Let's figure out what point B should be so that lambda, or like when lambda equals 2. So we're going to say xyz equals 1, 2, negative 3 halves plus 2, because that's lambda, 1, 2, negative 2. And that'll be equal to 1 plus 2, which is 3. 2 plus 2 times 2, which is 6. And negative 3 halves plus negative 4, which is negative 5.5. And this will be OB, or the position of point B. You could actually find also the point on the opposite side of the plane. So instead of putting 2 here, you could put negative 2. Okay, that's also a possible solution. Okay, 14. In each of the following cases, find the foot of the normal from A to the given plane, and hence find the shortest distance from A to the plane. So remember this form of an equation to define a plane. This is one point on the plane, 3, 1, 2. And then you use these two vectors, 2, 1, 1, and 4, 2, negative 2, multiplied times the scalars lambda and mu to construct a plane, okay? And first thing we'd like to do is we'd like to find the normal to this vector, or normal to this plane. Okay, so what we're going to do is we're going to take this vector and this vector, which define the direction of the plane or the orientation of the plane, and we're going to cross product them together. If we do that, then we'll have the normal to the vector, which is something we're going to need. 4 to negative 2. And so that's going to give us negative 2 minus 2, which is minus 4. And it's going to give negative 4 minus 4, which is negative 8, positive 8, because we take the negative of that. 2 times 2 is 4, minus 4 is 0. So the normal vector to this plane is negative 4, 8, 0. And now what we can do is we can find an equation for the normal vector line, which would be, let's see, x, y, z equals the point A, 3, 2, 1. And we're going to add lambda times the direction vector, negative 4, 8, 0. And this will produce three parametric equations, which are these. And z equals 1. Now what we normally do with these equations is we immediately plug them into the Cartesian equation for the plane, but we don't have that. We got this weird vector equation for the plane, but this vector equation did provide us with the direction vector of the normal, and it also provides us with one point on the plane, which is 3, 1, 2, right? So can't we just convert this into a Cartesian equation for the plane? We could. We could put negative 4, 8, 0, which are the coefficients for the normal, and then we multiply that times x, y, z, and the right side we multiply times 3, 1, 2, which is 1 point on the plane. All we need is 1 point on the plane, and then we add those together and we add those together. So we simplify it and we get negative 4x plus 8y equals negative 12 plus 8, which is negative 4. And then we can use this to find the lambda, which would give us the foot of the perpendicular just by plugging in these expressions for x and y and lambda. So we can put negative 4 times 3 minus 4 lambda plus 8 times 2 plus 8 lambda, and that is going to equal negative 4. Okay, and I don't like my lambda there. It looks too much like an x. That does too. Okay, and now I'm going to simplify. Negative 12 plus 16 lambda plus 16 plus 64 lambda equals negative 4. So let's group our lambdas together. That gives me 80 lambda. Let's group our constants together. That gives me 4 on the left side. If I subtract 4 from both sides, it'll give me minus 8. So our lambda is actually equal to negative 1/10. So if lambda equals negative 1/10, what is the location of the foot, we would plug it into here or into here and find out what our x, y, z's are. So let's see. Look at that, x 3 minus 4 lambda. So if we put negative 1/10 in for lambda, we would have 3 plus 4/10, which is 3.4. If we put negative 1/10 lambda here, it would give us 2 minus 0.8, which is 1.2. And of course, the last one would just be 1. So the location of the foot would be 3.4, 1.2, and 1. So that's the location of the foot. And then you're supposed to figure out, I think, the shortest distance. Yeah, now we're supposed to find the shortest distance. So the shortest distance would basically be if this is the foot, what we want is the distance of A to the foot. So first we're going to find the vector A to the foot, which is going to be 3, 2, 1. And we're going to subtract 3.4, we're going to subtract 1.2, and we're going to subtract 1. And that will give us negative 0.4, it'll give us 0.8, and it'll give us 0. Okay. And so if we wanted to find the distance, or the length of the foot, then we would just put that in Pythagorean's theorem. It would give us 0.16 plus 0.64, which would be the square root of 0.8. Okay, number 17. Find the distance between the parallel planes. X plus y plus 2z equals 4, and 2x plus 2y plus 4z plus 11 equals 0. The way I'm going to solve this is I'm going to write the normal line from this plane in vector form. So, for example, I am going to find the normal vector, or not the normal vector, the normal vector, direction vector, by looking at the coefficients here, 1, 1, 2. I'm going to write those as direction vector, the normal line. That makes sense, right? I'm going to multiply times lambda. And then I need a position vector. So the position vector could be any point on the plane. So a really easy point on the plane would be as if I put a 4 here and a 0 here and a 0 here. Do you see how that satisfies the equation? 4 plus 0 is 4. So that's a really easy initial position vector. I put that here, okay? So everybody agrees that this is a vector equation for a line that originates from point 4, 0, 0, which is on this equation, which is on this plane. And I am writing the direction vector here so that it defines every single possible point that is normal to the plane, and the foot would be this point. Okay? And now what I'm going to do is I'm going to change this into parametric equations like we sometimes do. So we're going to have x equals 4 plus lambda. We're going to have y equals lambda. And we're going to have z equals 2 lambda. Okay. Now that I have these parametric equations, I can do what I did in previous problems, and I can substitute these equations into the other plane's equations, and then this would give me a way of figuring out what lambda would be when this line crosses the parallel plane. So like, let's say that this is the red plane, and this is the blue plane. Okay, and so what I'm doing is I'm taking the red plane and the blue plane, which they told me are parallel to each other, and I could confirm it by looking at the coefficients. And I drew a line that's perpendicular to the red plane, like that. And what I'm looking for is, when does this purple line equal the blue plane? So what I do is I take the parametric equations for the purple line and I substitute them into the blue plane, and then I can figure out what value of lambda is when the purple line actually hits the blue plane. And that would give me another point to figure out the distance between the planes, because if we have this new point that's on the blue plane and we already have the point that we found, which is 4, 0, 0 on the red plane, we just need to figure out the distance between the two, which we can use the distance formula. So let's do that. I'm just going to erase this because it's kind of in the way. So we're going to put 2 times 4 plus lambda plus 2 times lambda plus 4 times 2 lambda plus 11 equals 0. So let's expand. 8 plus 2 lambda plus 2 lambda plus 8 lambda plus 11 equals 0. So 2 lambda plus 2 lambda plus 8 lambda is 12 lambda. 8 plus 11 is 19. So 12 lambda equals negative 19. Lambda equals negative 19 twelfths. So this point here that's on the blue plane can be found by doing 4, 0, 0 plus 1, 1, 2 times negative 19 twelfths. And so that would be equal to, it would be equal to this vector here. I just did a bunch of fraction, addition, subtraction. Now, actually, let's call this point A, and then we'll call the other point on the blue plane B. So A is actually 4, 0, 0, right? And this point we just found is B, right? But actually what we want is the vector AB, and it turns out that the vector AB is this here. This is the vector AB. So we didn't really have to find B. What we really want is this. So this is a very messy looking vector, but actually what we want is its length. Okay? So to find the length of this vector, all we need to do is take the scalar, which is 19 twelfths, and multiply it times the length of 1, 1, 2. So this would be the vector 1, 1, 2. So what is the length of 1, 1, 2? Well, the length of 1, 1, 2 is 1 squared plus 1 squared plus 2 squared, which is 6 square root. So our answer is 19 square root of 6 over 12. Okay, last problem, number 19. Find the equations of the two planes which are parallel to 2x blah 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 and 2 units from it. Okay. So again, we're going to look at the normal vector, which would be 2, negative 1, 2. And we would like to have two equations that are 2 units from this plane. So let's find one point that is on this plane. Let's use maybe 0, negative 5, 0. Okay, so 0, negative 5, 0. If we put that combination of x, y, z in it, we see that we satisfy the equation. So this will be the position vector, which we'll use to initiate our line. Okay, and this line is kind of like the normal line to this plane. And of course the normal vector is 2, negative 1, 2. Okay. So the question is, when does this vector, when is it exactly 2, or when is a point on this vector exactly 2 units from 0, negative 5, 0? Well, that would be when this is 2 units long. Okay, so let's see. So when is this vector 2 units long? It could be negative 2 also. Okay, plus or minus 2. Okay, so that would be 3, because 2 squared plus 1 squared plus 2 squared is actually 9, and square root of 9 is 3. So 3 lambda equals plus or minus 2. Lambda equals 2/3 or negative 2/3. Those are the two possibilities of lambda. Okay, and so let's see what are the 2 points that are related to lambda equals 2/3 and lambda equals negative 2/3. Lambda equals 2/3 we can find by doing -0, -5, 0, plus 2, -1, 2 times 2/3. And negative 2/3 would yield 0, -5, 0, plus 2, -1, 2, minus 2/3. So the first one would be 0 plus 4/3, which is 4/3. The second one would be -5 minus 2/3, which would be -17/3. And the last one would be 0 plus 2 times 2/3, so 0 plus 4/3. Okay, so that would be in the case of lambda equals 2/3. In the case of lambda equals negative 2/3, it would be 0 plus negative 4/3. And -5 minus 1 times negative 2/3 would be -5 plus 2/3. -5 is -15/3 plus 2/3, so it'd actually be -13/3. And then the last one would be 2 times negative 2/3, which is -4/3. Okay. Now what we're going to do is we're going to take our point that we found. So like basically these points right here are points that we know are unit 2 distance away from the plane. Okay, so one of them is here and the other one is here. We are going to define planes that go through those points. And the way we do that is we plug in our coordinates that we found for this point here. We're going to plug it into the plane equation. And what are the coefficients for the plane equation? Well, it's going to be 2, -1, and 2, just like this one because it's parallel, right? So that's what we did here. On the left side, we have 2x minus y plus 2z, which is the exact same thing as this one here, right? And then on the right side, we write 2x minus y plus 2z, but we substitute in 4/3, -17/3, and 4/3. When we do that, the left side stays as is. Now the right side becomes 8/3 plus 17/3 plus 8/3. When we add those together, we get 33/3, which happens to be 11. So that will be one of our plane equations. Okay? And then the other equation we would use, we would have 2x minus y plus 2z. On the right side, we would have 2, -1, and 2. And here we're going to put -4/3, -13/3, and -4/3 here. And we're going to add everything together, so that'll give us -8/3 plus 13/3 minus 8/3. And that would give us -16 plus 13, which is -3/3, which is -1. So our second equation would just be 2x minus y plus 2z equals -1. Oh, this one was equal to 11, right? Okay? So those are the equations for the two planes that are 2 units away from the original plane they gave us. Okay, that was page 5.